Okay, welcome everybody. I want to call to order this special meeting of the Santa Margarita Groundwater Agency Board of Directors, August 26th. It is 5:33. Can I get a roll call, please, Nick?
You absolutely can. And as a friendly reminder here, everybody has been muted, so you are going to need to unmute yourself. Let's just to start off, though, Director Engfer.
Present.
Director Leopold. Director McPherson. Director Cassidy.
Present.
Here. Oh.
Director Franklin. Okay, looks like we have a caller here. Sorry, folks, just give me a second.
Donna Lind.
All right, just got that was Donna Lind as caller 3. I'll mark you as present in a non-voting capacity for the time being. Nothing from Director Franklin. Director Pollock.
Here.
Director Dills. Again, you might need to unmute yourself if I'm calling you. Yep, gotcha. Director Ferris. Director Henry.
Here.
Director Stiles.
Here.
Director Perry.
Here.
All right, we're going to go through the alternates at this point. Director Baskin. Director Brown. Director Koopman.
Here.
Director Hayes. Director Lind, I already have you annotated. I do have you on mute, just for your awareness. Looks like you are going to be here in a non-voting capacity. Director Moran, and hold on one second. For Director Moran, I need to unmute you. All right, Director Moran, are you here, sir?
Present. Yes, I am here.
All right, got you loud and clear. I'm going to put you back on mute for the time being. Director Eckwall.
Present.
Okie doke. All righty, Chair Perry, we have 1, 2, 3, 4, 5, 6, 7, 8 folks in a voting capacity present at this time, according to my count.
Okay.
Nick,
All right.
could I ask you to state which alternates are in a voting capacity today? Because I think we have some.
Yep, absolutely. And again, I am seeing that Angela Franklin is here in the chat. Director Franklin, do you want to just state that you're here for the record so I can annotate you? I got you muted if you're trying to talk. I'm going to mute you.
Yeah, I'm here.
Okay, I got you there. If that's the case, I'm going to annotate you as here. Jeff, you were in a voting capacity until I got her down. Right now, it looks like the only alternate that we have here in a voting capacity at this time is going to be Director Moran from San Lorenzo Valley.
Thank you.
Okay. All right. Thank you, Nick. Do we have any additions or deletions to the agenda?
I just have a really quick note. I noticed on the second page of agenda, under the adjournment, it is noted that next scheduled board meeting will be in September because this is a special meeting. We will have a meeting tomorrow on August 27th. So just wanted to make you aware of that for the record.
Okay, thank you. Okay, oral communications on matters not on the agenda. Let me just say real quick, I'm glad to see everyone who's here. Obviously, all of our thoughts and prayers, mine personally, to everyone in affected areas, and very sobering time. But I'm glad that we're able to do this and move ahead. So thank everybody for coming. Anyone else from the general public who has a comment on an item not on the agenda? Nick will turn on the callers here and feel free to chime in.
All right, if you are calling via telephone, Director Lind, I have you up right now, and I'm trying to get back to Director Moran, you as well. If you have any comments at this time, you're welcome to share them.
Just from Donna Lynn, I echo what Director or Chair Perry said, that thoughts and prayers are with so many that have been devastated through this time.
All righty, thank you, ma'am. And Rick Moran, I have you up as well in case you want to say anything. If not, that's fine as well.
No comment.
Understood, sir. And for those directors calling in, I now have you back muted again, and I'm not seeing or hearing anything else from anyone member of the public. If you're a member of the public and you're on the web, feel free to go ahead and unmute yourself and share any thoughts that you have at this time. Okie doke, hearing none and seeing none. Chair Perry, back to you, sir.
Okay, thank you, Nick. Okay, we have the approval of the minutes of the July 23rd board meeting. Do I get a motion from anybody?
I will move adoption of the July 23rd minutes, and this is Jack Dillis.
Thank you, Jack.
I will second.
Second. You win.
I think Dale was the second, am I correct? Okay, Dale raised a finger, so Dale Pollock is the second. Okay, do we have any comment from anyone in the public who read the minutes and disagrees? Okay. Seeing, you unmute.
Yep, I'm going to go ahead again. I'm just going to do Director Moran here because you are attending in a voting capacity. Sir, you're unmuted at this time. If you have any comments on the minutes, this is the time.
I have no comment.
All right, thank you, sir. I'm going to go ahead and put you back on mute then. All right, and understanding there are no other callers here from the general public, both of the
Okay.
callers are alternates. So.
Okay.
Yep.
And I'm not seeing any comments from any of the board members in the chat, so I'm going to assume that everyone's good with it. Can I get a roll call vote?
Sure can. And again, just a friendly reminder to check your mute buttons on this one. Director Engver.
Yes.
All right. Director Leopold is not here. Director McPherson is not here. Director Cassidy.
Yes.
All right. Director Franklin.
Yes.
Director Pollock.
Yes.
Director Dillis.
Aye.
Director Ferris is not here. Director Henry.
Yes.
All right. And hold on one second here, and let me just go ahead and unmute. Apologize for the delay, folks. All right, Director Moran, can I get your vote on item 2.1, please?
Yes.
All right, I got you, and I'm putting you back on. All right, Director Stiles.
Aye.
Gotcha. All right, and Director Perry.
Aye.
Okay,
Hey.
looks like the motion passes.
Okay, excellent. So we have the reappointment of well-owner representatives for the term ending August 27th, 2023. Is there, I mean, I think we all know what this is about. Does anyone have any questions? Okay, do I hear a motion? The motion would be to reappoint the fabulous directors of the private.
I will
Well-
make a motion. Lois Henry.
Could you
To
please call out?
reappoint-
Yeah.
What?
the two. Yeah, just make sure you name the two representatives whose terms are up, please.
Oh, well, They aren't
It's
there.
Eden Cassidy and Angela Franklin.
I think Lois is,
Reappoint Directors Cassidy and Franklin of well owner representatives for a term ending August 27, 2023.
I'll
Okay.
second.
Ruth seconds those wonderful people.
okay. Jack was a close second to your second, but Ruth Stiles wins.
Okay.
Okay. So I'm gonna, I guess we'll open it up. Is anyone here from the public, Nick?
Yeah, we do have one or two.
Okay, so let's open it up to, I see, sorry, so hand wave. Let's open it up for public comment.
Right, just a friendly reminder here, if you're joining us on the GoToMeeting app, you are going to need to unmute yourself in order to make a comment. This is the time at which you are welcome to do that, should you have one. And likewise, I'm trying to find, all right, and Director Moran, you are unmuted as well, just in case you have anything to contribute to this conversation, sir.
I do not.
All righty,
Okay.
Director Perry, I'm hearing none and seeing none.
Okay, excellent. So let's take a roll call vote in that case.
Gotcha. Director Rank.
No comments from the board in the chat
Oh.
box. Yeah, take a roll call
Yes.
vote, please.
All right, gotcha. Director Rankford, I have you down as a yes. Director Cassidy.
Is it appropriate to vote for myself? I don't,
Unless you don't like yourself.
oh, all right. I'll vote yes.
All righty, I got you. Director Franklin.
I'll vote for Eden and he can vote for me. Yes.
That sounds equitable. All right, Director Pollock.
Yes.
All right, Director Dillis.
Yes.
And, Director Henry.
Yes.
And Director Moran, let me just make sure you're unmuted. All right, Director Moran, how say you, sir?
Yes.
All right, Director Stiles.
Yes.
Director Perry.
Yes.
9 votes out of 9, unanimous.
You're stuck, Eden. Okay, that's great. Thank you. Okay, let's move ahead to number 3.1. This is our informational session. Climate change scenarios, groundwater modeling. California State, we have Sean Chartrand, Balance Hydraulics, and Cameron Tanya of Montgomery and Associates. I guess we're gonna start with Sean. So take it away. Take control of the screen.
Sean, I just gave you presenter rights. It is all you, sir. Let me, I can't unmute you for whatever reason here.
I apologize for mangling your name if I did.
I think I just unmuted myself. And you said my name perfectly. Thank you.
Okay.
Although it is Balanced Hydrologics.
Hydrologic.
Very common mistake though. First off, I just would like to extend my sympathies and thoughts for all of you in the greater Santa Cruz region. You're in my thoughts daily, and I'm sending you all strength. It's very nice to be here with you this evening and follow up from what I thought was an enjoyable discussion we had back in December. And the purpose tonight is to focus in on the projection that has been selected for use in the groundwater model to evaluate how the system may respond to a future climate. So I'm going to share my presentation now. As we go through the presentation, I have embedded a few slides that have an obvious question in the slide content. It's about every 5 slides or so. I put these in at roughly at points where I thought were good stopping points where we could field questions. But by all means, if you have a question prior to that, I'm fine if you speak up. I don't have a problem stopping. So I'm just going to switch views here and let me know that, oops, sorry about that. Hang on a second. Does everyone see the presentation on my screen?
Sean, we were able to see your presentation. It just
Okay, great.
now.
How about
It was a silent agreement by all.
excellent. When I switch back, will someone just talk up and indicate that you see it? Thank you.
I'll go ahead and take care of that. Yep.
Okay, thanks. Okay, can you?
So right now I just got you. Doesn't look like your screen is currently shared.
Oh, weird. So all you see is me, is that correct?
That is correct. Yes, sir.
But you could see it prior to this.
Sure could.
Oh, interesting. Why don't you? Oh, I see why. For some reason it shut off. Okay, there we go.
Okay, now we're in business.
Great. Okay, all set?
Good to go.
Okay, so tonight we're going to review what's called the GFDL Climate Model 2.1, the A2 scenario. And I'm going to explain in I think a fair amount of detail what GFDL is and what CM 2.1 is and what A2 is. And in addition to that, I'll give you a few glimpses of how that was applied, in this case, to the City of Santa Cruz work. We did talk about that in quite a bit of detail in December, so I think we should be good there. I just have a few slides to remind you of that process. And then I'll spend a little time comparing the specific results of using this projection to results garnered from using other projections. And I'll end with just a few items of what we learned in the process. So just as a quick reminder why we're here, so as a part of the GSP planning process, we need to use climate change projections and evaluate how the system may respond to future plausible climates. I'll use the word plausible here because there are many future climates that are possible. Our goal here is to use one that experts have deemed is plausible, and that's how we've gone forward. We talked in December a little bit about the difficulty associated with that, as the figure here shows. This would be a projection period for the time October 2019 through September 2069. And on the y-axis, we have total annual precipitation in inches. What I'm showing you here are 10 different projections of total annual precipitation over that time period, all plausible projections of precipitation. So in December, we talked a little bit about the fact that this introduces difficulty in selecting a projection to use for the present purposes and for any climate change planning purposes. And in this case, we've gone ahead and we've selected one particular projection to use. And we'll talk a little bit why we selected that projection. But this is just as a reminder. Okay, I don't think we'll have any questions up to this point, but before we launch into it. Okay, great. Okay, so the projection we're using is developed in the Geophysical Fluid Dynamics Laboratory. It's called a coupled model. That means the model couples the ocean and the atmosphere, and that is in general what produces what we call a general circulation model. This is just a video of the updated version of the model that we are presently using for the GSP. This is the GFDL coupled model version 3. I'm showing this video to you just to show you that these models are capable of elaborate and highly complicated simulations of the Earth system. This model in particular is showing you how annual surface air temperatures and the extent of sea ice is changing in response to a changing climate. These models have been in development for now about 3 decades or more, and they undergo a significant peer review process. The end result of that is what we have used for our application. If you want to learn more information in particular about the Geophysical Fluid Dynamics Lab, which is a component of NOAA, I've given you the website here. You can go and check out some more details there. The GFDL coupled model XX, meaning they have multiple versions at this point, but the version 2.1 is a core model of the NOAA Fluids Lab. Its development, the development of the present model structure, I should say, began in the late 1990s, and the goal with developing the model was to provide a unified framework to the missions and goals of the broader NOAA organization. Version 2.1 goes back some time now. It goes back more than a decade. But at the time, version 2.1 was one of the main coupled atmosphere-ocean general circulation models that was used to develop the Intergovernmental Panel on Climate Change Assessment Report number 4, and that report was released in 2007. After the report was released and after the results of that simulation went through peer review, through what's called the CMIP process, the Coupled Model Intercomparison Project, where they run a whole bunch of climate models using the same boundary conditions so they can assess how sensitive each model is to different climate conditions. The state of California adopted those results. It went through their own peer review process in California. Those results were then published, and then we use them for work with the city of Santa Cruz starting in about 2010. The GFDL coupled model is, as I said, a core model to NOAA's purposes, but the infrastructure of the model has been in development for quite some time. It's called, the core of the model is called the V3 model, or they call it the dynamical core. I'm just highlighting the point that the basic part of the model that we use the results from serves as a base core for many different models at the Geophysical Fluid Dynamics Lab. And most recently, the core has been adopted, and it's now being used, for example, for real-time forecasting with global weather, where they run this model twice daily, and that's a joint collaboration with NASA. So the real takeaway point here is these are highly sophisticated models of the Earth system. They've been in development for quite some time, and their goal is to build a base infrastructure that they can utilize across many different models. And in our case, the model version 2.1, we benefit from all the work that's gone into it, and the projections that come out of it are a reflection of that significant effort over, at this point, 3 or more decades. California chose the GFDL version model 2.1 among 3 other models at the time, so this is back in 2010, for 2 reasons, mainly because it produced reasonable simulation of key features of observed climate in California, as well as reasonable representations of the Pacific ENSO variability. At the time, it was also useful because it had data that was available at the daily and the monthly time steps. Not all models at that time were producing data at the daily time step in particular. The screenshot on the right is what the CalAdapt website looked like in early 2012, just to give you an idea. It's changed quite a bit. It's a much more powerful tool these days. But at the time, this is the portal that we used to extract or download the data that we ultimately ran through the model that we developed for the City of Santa Cruz HCP process. So are there any questions with this?
is he on mute?
Sorry. Just curious. So the ocean temperature is measured by satellite, I would imagine?
I guess what's the context of your question?
I'm just curious because I know I'm just curious at what depth the measurement is. Is it an average from, surface temperature to a foot below or something like that?
The data that is fed into the global circulation runs?
Yes.
That's a good question. The model has a vertical structure of, I believe, 24 elements in the atmosphere at this point in time. I'm not sure the vertical structure in the ocean, but of course at this time it's changed over the last decade for sure. But there
Sure.
are observations made at many different depths in the ocean so that they can get a decent representation of temperature gradients at different locations and what
Right.
the fluid dynamical properties are of the ocean given certain climate conditions. But
Great.
beyond that, yeah.
Okay, good. I'm just curious. Average sounds like a certain
Well,
decided upon average and they stick with it.
it's a finite volume model, so everything is going to be averaged over certain volumes.
Okay, great. Thank you.
Also, just as a additional one, Director Moran, just because you're calling in, I have you up if you have any questions.
No, I do not.
All right, thank you, sir.
So I'll take it that's all for now. All right. Okay, so that's a little introduction to the model itself. And we'll spend a few minutes talking about the emission scenarios. So at the time, so again, the version 2.1 model was used as a part of the IPCC assessment report number 4, which was published in 2007. Prior to that, the IPCC put out a report called the Special Report on Emission Scenarios that was released in 2000. And these emission scenarios are what were then used in the 2.1 simulation in terms of climate forcings. The fourth assessment report scenarios were considered baseline scenarios at the time because they did not take into account future possible actions by governments, say through the Paris Accord or things at the time that were unknown, but perhaps people had it in their mind they would happen, but they didn't want to make any assumptions related to direct actions. They did make assumptions about population growth, technology, general technology advancements, how segregated the world might become, and so forth. In all of the scenarios, the general gist in terms of global GDP, so you have some sense of what they were thinking in the late 1990s, is that the growth factor would be about 5 to 25 with the emission scenario. So there would be a range of continued growth in world output in terms of economic output. And with this version of the global circulation model results, the emission scenarios emphasize trajectory of greenhouse gas emissions, and that differs from what is used today. But on the right, we see 4 plots. We have carbon dioxide, methane, nitrous oxide, and sulfur dioxide. These are the 4 primary greenhouse gases represented in the model. And you can see the range of responses or trajectories over time that these various emission or these constituents were assumed to have over a time period out through 2100. The A2 scenario, if you can see my mouse, you should be able to, is this orange curve here. We're in the carbon dioxide plot. You can see that it's a general upward trend all the way out through 2100. Same goes with methane. Same goes with nitrous oxide. Here's a little context for the different emission scenarios. Our focus today really is on the A2 emissions. At the time, they classified the A2 emission scenario as a regionalization response in the world with more economic focus. So in general, the A2 emission scenario at the time was given the title as business as usual. So even though the world was going to become more segregated so that we'd have more regionalization of economic output and population growth, the emissions were expected to continue on pace as we understood them during development of the emission scenario. So there would be no abatement of emissions out through the projection period, and that's what you see here in the curves of the different greenhouse gases. They continue to rise out through the emissions, or I'm sorry, out through the projection period. Oh, I should say also, at the bottom of each square here, we see the range of temperature increases associated with the different emission scenarios, depending on which global climate or global circulation model you look at. And we see with A2, the range in temperature increases out through 2100 cover the range of 2 degrees Celsius up through 5.4 degrees Celsius. So at the time, the A2 scenario, as I said, was business as usual, but it was also generally associated with fairly high temperature increases out through 2100.
We have a
Questions?
question from Doug Engfer.
Hey, Sean, this is Doug Engfer. So there's been a little bit of time passed now, and I see that 2020 is part of the way across the scale here. And there's some windage between the different models as they track the different greenhouse gases. Care to comment on which of these scenarios is tracking most closely to ground truth?
Doug, that is a great question, and I think the next slide actually answers that question. So if there are no other questions or comments here, we can go to the next slide.
Yeah, there are no other questions.
Well, I'll pop ahead a slide and then we'll go back. So here's the answer to your question, Doug. So on the y-axis, we have year, and this is a paper that was published just in 2019 December in a journal called Geophysical Research Letters. I'm happy to circulate the paper to the group if it's of interest. The papers may be of interest because what they focus on is a performance evaluation of past general circulation model results with respect to what we're actually observing. So your question is quite pertinent, Doug, for where my brain was when I was thinking about putting this together. On the y-axis, we have temperature anomaly. So this would be a departure from an average over a historical time period. In this case, I believe the period that the authors focused on was 1950 through 1999. So in the blue curve, we have global observations of temperature, surface temperature, I should say, on the planet. And this would be expressed, as I said, as an anomaly. And the black curves represent different scenarios loosely associated with general circulation model scenarios. So in this case, the dotted curve, scenario C, is considered a low emissions trajectory. The dashed curve is considered a moderate emissions trajectory, and the black curve is considered a high emissions trajectory. So I think in very loose terms, the A2 emissions scenario would be most similar to scenario A, and a different emissions scenario, B1, I believe, would be more similar to scenario C. We can see, in fact, that the global observations, when we boil them down to averages, track this scenario C quite closely, and 2020 sits just off this plot because they published their paper in 2019, but you can see at this time in general, we're looking at roughly a 0.6 to 0.8 temperature anomaly, and that's pretty well bracketed by scenarios C and B. Does that answer your question, Doug?
Yes, it does. Thank you very much.
You're welcome. And I will say at the time we chose GFDL A2 because, of course, people's perceptions and perspectives and thoughts about how emissions will change over time. Back in 2008, 2010, when we got serious about using climate projections in the HCP process, there was still quite a negative vibe in the scientific and the policy community, and that tended to attract us to higher emission scenarios, in large part also because they were associated with higher temperature responses, global average temperature responses. So here's just a little more context for the A2 emission scenario relative to the, in this case, two other scenarios, A1B and B1. We can see that A2 here is indicated by the red curve. We have year on the x-axis and global surface warming on the y-axis. Again, this global surface warming is expressed as a temperature anomaly. So a increase of temperature relative to some historical average. And clearly in the plot, you can see that A2 is quite warm relative to A1B and B1. These three scenarios in and of themselves, A2, A1B, and B1, represent special scenarios that the IPCC was interested in for the assessment in the assessment report number 4. So there were other emission scenarios, but they considered these three to be representative of the range of conditions that could be expected. And so the assessment report really focused on these three emission scenarios. There is an emission scenario that does produce much higher temperature warmings over time, and that's this A1F1. That's considered at the time was considered a very extreme emissions trajectory, and of course it drove a quite strong temperature change over time. Just making note of that. Okay, so we covered this. Just to put things in a different plot here and bring it home a little bit. So up till now, we've been looking at global averages. Here we're looking at projected temperature changes, and again, as an anomaly for the state of California. So this would be average temperatures for the state of California. Our focus here is on A2 and the GFDL 2.1 model, which is shown here in this orange curve. So you can see relative to the 8 projections plotted here, it's in general the third warmest by the time we get to the end of the projection period. It's classified as a medium to higher warming scenario. And as you can see, also things are capped here by this A1 HAD CM3 model. This model in general produces warm climates over time as far as I've seen over the last 12 years of looking at data. But anyway, so this is the climate or the California context, and our focus here is on this orange curve. So we have understanding at home, we should expect warmer temperatures or temperatures in the, I guess, higher warming relative to other models when we apply this projection to our work in Santa Cruz. Any questions with this?
Lois has a question.
Lois, I think you're muted there.
Yeah, I unmuted. Recently, I saw the highest temperature, I think, in Death Valley that has ever been recorded. What was it, 130 degrees or some huge amount?
That's correct.
And do you think that is going to wind up being normal or even higher?
Well, that's a great question. You know, I don't know if I'm in a position to really wager an opinion there. I will say that Daniel Swain at UCLA, we talked a little bit about his work during the December meeting. He's put out a couple he's been interviewed and also, I think, posted a blog about the recent heat wave and how he views that with respect to climate change. And after this meeting, I'd be happy to also share those links through Nick with all of you so you can read for yourself what he thinks. I think in general, just the boilerplate answer is it's clear the planet is getting warm, and it's getting warmer in many places in the far north and now in the far south at rates that are much more rapid than what climate models had projected even a few years ago. So, I think it's fair to say that we can expect much warmer temperatures in the future. Whether or not 130 degrees in Death Valley and a few other places becomes a new normal during the associated summer months, it's difficult to say, but certainly we can expect much warmer temperatures.
Thank you.
Yep.
Just as a further admin note, if you're on the board of directors calling in, you are unmuted in case you have any questions. All right,
Okay.
hearing none and seeing none.
Okay. Let's see. All right. So at this point, that's my summary of the GFDL coupled model version 2.1 A2 scenario. So now I'm going to sort of focus things in on Santa Cruz and how we've applied that in the past. And so I guess just one more opportunity for people to ask questions before we shift gears here a little bit. Okay. So in the December meeting, we did talk a bit about how we use climate projections within the HCP context and now within the broader water supply planning context with the city. And in general, what we do is we use an empirical-based model to develop projections of stream flow at this point in time for the future period 2020 to 2070. It's kind of exciting to do that. And now at this point, we have 10 years of model simulations. And since we're in 2020 now, we have a chance we can look back and evaluate how some of those projections compare to what we're seeing today. I will say, I'm not going to show you those results today, but a little surprisingly, the model, or I should say the projections we used, are pretty consistent with what we've seen through this first half of the first 9 months of water year 2020, which is, that's confidence building, could be serendipitous, but it's interesting nonetheless. For our work with Santa Cruz, that's relevant for our purposes today, we do project stream flows at the San Lorenzo River Big Trees gauge, and the work that goes into doing that and the climate projection, in this case the A2 GFDL scenario, this is the data that then has been transferred over to Montgomery Associates, and they've worked with that data and have begun to get it ready for incorporation into the groundwater model, and I think Cameron may talk a little bit about that today. In general, we feed the projections into a water balance model that ends up producing a projection of stream flow. We take that projection of stream flow and we partition it in two ways. Part of it goes to water supply, but the part that goes to water supply is conditioned on a requirement for in-stream flows for Steelhead and Coho. And those in-stream flows at this point are quite complicated. They vary depending on which stream we're applying them to. They also vary depending on how wet or dry any given year is, and they vary depending on what month we are in. So it's a process that's evolved over, at this point, 14 years of consultation with NOAA and California Fish and Wildlife Service. And this is the general framework that we have used these projections in, and now that the GSP is benefiting from all that effort. Before we use the GFDL A2 projections in our previous modeling, we did go through a process of adjusting the data. So here's a plot. It's showing you precip in feet per day for a 50-year period. So at the top we have historical data. This is for the CRZ station located up in De La Viega Park. In the middle is the raw climate change data, or the raw projection data from the GFDL 2.1A2 scenario. And this middle plot, what it represents is the data that I actually downloaded from the CalAdapt website and then simply plotted it. In the bottom plot is something that we called the transient data, and this data was produced by Stratus Consulting. Some of you are familiar with them. They're a team that led the WASAC effort, or the Water Supply Advisory Committee effort for the city of Santa Cruz. And the reason we went through the process of modifying or adjusting the raw data is because a large climate change planning effort that was conducted in Colorado came to the conclusion that global circulation models that were downscaled according to a certain downscaling technique ended up biasing results, in this case precipitation, to be wetter than should be expected. And they documented it in a fair amount of detail in their report. This citation on the right takes you to that report. You can read it for yourself. In the end, what we ended up applying is something called a delta method of rescaling the data. And all we're simply doing is we're adjusting the raw data for how wet the data is relative to the modeled historical period. And then we simply apply that scale to observe precipitation values in the watershed. So just looking at the middle plot and the lowermost plot, you can see that the adjusted or the transient data are quite a bit drier than the raw climate change data. This drier record is within the expectations of what people, climate scientists at the time, would have otherwise expected the downscaled data to look like in terms of its general statistical character. Just to give you a sense, a deeper sense of the information. So here's a plot of the historical stream flow at Big Trees, and it's represented by the orange curves. And what we're looking at here is total monthly stream flow, and I've ranked that data from lowest flow to highest flow. And in the blue, this is the GFDL A2 modeled total monthly stream flow. And you can see that in general, the modeled stream flow tracks the historical flow quite well, except we get a departure here during what are the very wettest conditions, and the very wettest conditions in the model data are quite wet relative to what we've observed over the 50-year compared period at Big Trees. If I zoomed in on the lower or the driest conditions, you'd also see that the model data are relatively wet compared to what was observed at Big Trees. So we see that the raw data is in fact, when we convert precip to stream flow using our water balance model, we get a quite wet result. This is the result when we convert or we adjust the raw precipitation record and the raw air temperature record for this bias that I just spoke about. And in the end, now I'm just plotting a comparison between the observed record and the modeled record, and we can see that the adjusted data give us a much drier condition. So this line here that shoots off up the middle of the plot roughly would be a 1-to-1 correlation between observed and modeled. In fact, we're well shifted below that 1-to-1 line. So our new projections of stream flow are quite dry. In general, they're roughly about a factor 3.5 drier than what we've observed in terms of total monthly flow at Big Trees. And I have not shown you the wettest conditions, but this trend more or less continues along this trajectory for the wettest conditions even. I imagine there might be some questions with this.
No one has chimed in from the board on the chat feature.
Okay, great. Okay, so now we're sort of going to wrap things up here, and I'll give you a basic look at how the GFDL model version 2.1 A2 projections compare to some other projections. At the December meeting, if you recall, we spent quite a bit of time looking at a plot that looks like this. I'm going to focus on this type of data communication in just a second, but just to remind you, when we do look at it, everything in the upper left quadrant is going to be quite dry and warm relative to historical average conditions. In the upper right, it's going to be quite wet and warm. In the lower left, quite dry and cool. And in the lower right, quite wet and cool. And when we get there, we're going to be looking at precipitation on the x-axis and air temperature on the y-axis. For that, though, we're going to look at some plots produced by Cameron and Georgina. They're quite useful. They did this work as part of the Mid-County Basin groundwater effort. And what we're looking at here is time on the x-axis, extending out through, I believe, 2100. And precip on the x-axis, and the precip is in inches per day. The GFDL version model 2.1A2 scenario is this red curve. The rest of the data plotted here, with the exception of the observation, are simulations produced by a later set of global circulation model work. So it's a more updated version of past models, but I wanted to use these plots because it provides a nice comparison between GFDL and a whole range of other model output. Looking at the observational comparison, you can see that there is a mismatch between GFDL and what we've observed in the basin itself. This level of mismatch is not uncommon between general circulation models that have been downscaled to local regions. In general, this would be an acceptable level of mismatch. And also in general, we can see that GFDL, in terms of precipitation, it bounces around relative to some of the other models. We have some quite wet years, but we also have some relatively dry years. But if we fit a trend line through here, I think we could convince ourselves that GFDL is roughly within the middle of the band of data that's plotted here for the other simulations. Georgina and Cameron also provided a monthly plot, so we can see how things compare at the monthly time step, which is quite useful. We see in general in the winter, GFDL can be a bit wet relative to the other four models plotted here, and in the early spring it can be quite dry. This early spring signal is in part related to the conclusions that have been reached now for quite some time that we can expect an earlier dry back or an earlier onset of the dry season heading out into the future relative to what we've experienced in the historical conditions. Then there is also this interesting signal of wetter events heading into the early fall. But in terms of climate change and in-stream flows and groundwater sustainability, groundwater recharge, having a strong departure in the negative in the March, April, May timeframe relative, in this case, to other models indicates that GFDL would provide quite dry conditions in that period of time. Here's the temperature plot. We're looking at minimum temperature from the model, and so this will be average minimum temperatures. And we can see in general that GFDL compares to the other 6 models shown here. It's quite cool in general relative to some of the models as we get out towards the end of the century. And relative to the observational record, it's also quite cool. Things change a little bit when we look at the max temperature. So the max temperature, again, we're looking at the red curve here. As we trend out towards the end of the century, we can see GFDL starts to be quite warm. And now this relates back to the earlier information we were looking at, where we had a range of, say, 2.9 to 5.4 degrees Celsius warming out through the end of the projection period, when in fact we're seeing that play out here in this plot. And by the end of the century, we can expect that the GFDL A2 simulation would be quite warm relative to many models, other models we could use. We see in a monthly comparison, this plays out in the May through September months where things get quite warm relative to the other 4 simulations that they've compared it to. However, heading into the early spring, it dips down and it's quite cool relative to those models. So this is a plot we looked at a bit in December. I thought it'd be useful to revisit it. This is a little bit more of a sophisticated way of looking at the data so we can get a sense of how precipitation and air temperature vary with respect to other simulations. On the left here, we have what's called the gridded historical data. So this is where the GFDL 2.1 model was run using climate conditions for the historical period, in this case 1950 through 1999. And so in a sense, this simulation is a test of how well the model reproduces the observed climate. In the previous plots, we saw that we can have some departures in that simulation from the observed climate, but in general, it was deemed reasonable and acceptable. The blue plot here is the scenario of interest for our present purposes. This is a GFDL 2.1A2 scenario. And the orange plot is something we call the 4-model ensemble, where we build a statistical ensemble of future possible or plausible climates from 4 different climate projections. And this red plot is something I believe you've heard a little bit about from Cameron and Georgina, perhaps. It's called the historical catalog. So in all 4 plots on the x-axis, we have precipitation departure. It's expressed as a ratio in this case relative to a historical precipitation average. And on the y-axis, we have air temperature departure. Again, it's expressed as a ratio of projected air temperature relative to an historical average temperature. And these results here are that we're looking at are for the winter, late fall winter months only. I've excluded the summer months from here, so the results extend over the period November through April. Because at the time with the city work, we were most interested in how the winter conditions might change. So we can see in general that GFDLA2, the core of the data or most of the data during the winter months plots as in the less precipitation regime. So we're in general less precipitation and much warmer, or warmer I should say, relative to the historical average conditions. Precipitation departures really range from 0 to roughly a value about 0.9. So in general, the precip departures can be quite extreme relative to historical conditions. And here would be the wetter months in the record that bring us out and make us wetter than the historical average condition. Almost all the precipitation is received within an air temperature regime that is warmer than historical average conditions. That is quite different from, say, this model projection where precipitation is received over a range of air temperature conditions from quite cool relative to historical average to quite warm. And that would be most consistent with the historical catalog, which is also quite warm and quite dry relative to historical conditions. So the key takeaway with this plot here is that we understand, and that really builds from all the prior plots, that with the GFDL 2.1A2 scenario, we should expect drier conditions with the model simulations under a temperature regime that can be quite warm relative to historical conditions. So I'm going to show you some results from work that Gary Fisk produced as a part of the WASAC committee. So some of you are going to be quite familiar with these plots. And the WASAC, again, is the Water Supply Advisory Committee that was convened to assist the city of Santa Cruz with water supply decisions and planning that was being conducted from roughly, I believe, 2012 through 2015. The plot here shows a comparison of the observed flows at Big Trees in the red curve, and this would be for the time period 1950 through 1999. So it's, yeah, I believe that's correct. Yeah, that's right. Well, no, this would be 1937 through 1999. And in the blue curve is the GFDL A2 projection of stream flow. And all we've done here is remove the years, and we're just looking at the months out from some start date. And the projection goes through 50 years. In general, you can see that the projected flows at Big Trees are quite dry relative to the historical observed flows for a comparable 50-year period. Even though we have in the prior plot here, we have some conditions that are quite wet relative to the historical average. It in general does not produce flows that are anywhere near the peak flows that we observed for the comparable 50-year period in the historical record. However, the minimum flows that we see with the projected climate scenario is on par with the lows that we observed in the comparison or the comparable 50-year period with the observed record at Big Trees. What does this mean for water supply in the case of Santa Cruz? So you can start to gain some intuition about how this might affect recharge, say in the groundwater basin. So the blue curve represents the historical peak season shortages for the city, and the red curve is the equivalent peak season shortage now for the projected climate. And that's for the projected climate, and it's a little confusing because the colors change here relative to this plot. But for example, if we look at the historical condition, we could expect a 20% peak season shortage roughly for 1% of the years for this analysis period. If we factor in climate change, we can expect a 20% shortage creeps up to roughly 8% or 10% of the total time over this 50-year period. So we can see immediately that climate change has an appreciable effect on projected water supply conditions for the city in the case of peak season shortage in this example. And that is associated with the likelihood of more or increased shortages in water supply. And in this case, we can just translate that into increased shortages of water available for recharge into the groundwater basin. I will just note that these results were produced in 2015 under the thoughts and perceptions and ideas related to what kind of infrastructure and other water supply projects the city might be pursuing at that time. And of course, those the details of that have changed in 2020. But this was the picture of water supply in 2015 related to the GFDL A2 scenario. So in general, what we learned that this is essentially the same set of conclusions we discussed in December. Hotter and overall drier is quite likely. We now have a greater appreciation that it's likely to be punctuated by a greater frequency of large storms. And in fact, we've experienced that regionally in the last 5 years. From our habitat modeling, we know that steelhead and coho will be more stressed relative to historical conditions, just based on the raw projections themselves. The previous plots indicate that water supply, and by analogy, water available for recharge will be more stressed relative to historical conditions. And with that, we can take some more questions.
Nothing in the chat feature from board member. Doug. Doug has a question. Doug Anker.
Thought you were going to get away with it. Sean, I know that fog is tricky business, as grateful as we are for it right now under current conditions with the fire and so forth. What's the state of the art or state of thinking on our ability to understand and predict what's going to happen with the coastal fog here?
That is an excellent question, Doug. I think we have, as my understanding goes, we have kind of two different strands of work that's being done. The work related to the items we've just discussed are framed within the context of general circulation models that are, of course, run over the globe. Those models, as far as I understand, are not in a position yet to really produce results that are relevant to the question of coastal fog. I believe there are other research groups, though, now that are taking regional climate models and trying to better represent the effect of a changing climate on fog. And those things that are going to be relevant there are, of course, ocean circulation conditions at the boundaries of their regional model, whether or not we get strong upwellings, what the temperature gradients are going up and over the Santa Cruz Mountains into the Santa Clara Valley, and what the urban island heat effect might be in Santa Cruz proper, creating, of course, large updrafts of warm air that can pull cool coastal air in. But as far as I understand, I don't know as of yet anyone that's producing, say, quote unquote, projections of what the future fog conditions may be. But the point is well made, and everyone should just be aware that these projections and simulations implicitly and explicitly do not account for anything related to fog.
Dale has a question.
Sean, I might have missed this, but did you say the amount of precipitation likely to decrease, or is it that the relatively the same amount of precipitation, but just coming in shorter periods or shorter time frames?
Yeah, good question. I probably confused everyone there because I started to intermingle different scenarios. For GFDL 2.1A2, it's flat, just drier, and we can see that. Where is that result? Sorry, give me a moment here. Okay. We can see that result here. So the blue curve is the climate projected monthly total flow at big trees, and the red curve again is the historical observed for the period, I believe, 1937 out through the end of the 20th century. In general, we can see the climate projected flows are very dry relative to the observed historical flows. So GFDL A2 model version 2.1 is just across the board dry. This stands in contrast to the more recent work over the last 5 years, some of it by this researcher named Daniel Swain, that helps to fill in the gaps around the future projected precipitation, where we can expect, in fact, fairly intense wet periods interspersed with longer dry periods. And I just raised the comment that that's in fact what we've seen play out in the region over the last 5 years. So we have two different things going on here. We're using a projection for the GSP purposes that is across the board quite dry, but newer projections inject this idea that we'll have intense wet periods interspersed with pronounced drier periods. And this is what people have now termed this climate whiplash effect, where we're bouncing back and forth between relatively wet conditions to relatively dry conditions. That's not represented in the GFDL 2.1A2 scenario.
Okay, Jack Dillis has a question also.
Yes. What about the increase in the ocean level? I know Doug brought up the issue of question about fog, but it makes me think of the ocean that's supposedly going to be going up. Would that have changes that could impacts on us that could, help us in some way relative to our precipitation?
I think Cameron can better speak to the effect of increase in sea levels and how that relates to our current purposes here of the Santa Margarita GSP. For the simulations that I've conducted or the model runs that I've conducted, an increased sea level has no bearing on our results. You are correct. Obviously, sea level is going to go up, but for the hydrology explicitly, it's not a real consequence. Now, whether or not there's more evaporation from the ocean certainly is a factor, and that is reflected in these general circulation models that are then downscaled to produce the data that we use. But you might want to ask that question to Cameron and see what he thinks in terms of how increased sea levels may affect conditions for the Santa Margarita Basin.
Okay, thank you.
Yep.
Thank you, Jack. All right, that's the only question.
Excellent. That's all I have for this evening.
Just a quick point here. Just want to circle back real quick, Director Moran, just because you're the one calling in. I just want to double check that you don't have any questions or comments.
I do have a question and a comment. A lot of this presentation is about the production of water, and I know the Santa Margarita is mostly concerned about storage of water. It seems to me that we're going to have to reevaluate consumption of water. Thank you.
That's a good comment. And just parenthetically, I will say that this peak season shortage result I'm showing you does reflect a specific assumption about consumption within the city of Santa Cruz.
Next, should we see if anyone from the public has a question at this point, or is it?
Yeah, if you're a member of the public here and you're joining us via the GoToMeeting app at this time, feel free to unmute yourself and share any comments that you may have on this item. We'll do this again, I'm assuming, after Cameron Tanna's presentation as well. But at this time, if you're a member of the public and you wish to comment, this is your opportunity to do so. All right, the only two callers that I'm showing right now are going to be Director Moran and Director Lind. Director Lind's not in a voting capacity, so I'm going to keep her muted pending your direction, Mr. Perry. And at this point, I'm hearing none and seeing none in terms of public comment.
Okay, thank you. Okay, thank you very much, Sean. That was great. Excellent presentation.
Well, you're welcome. I hope everyone has a better appreciation for the specific scenario that Cameron and Georgina will be using in their groundwater simulations.
Okay, thank you.
Yep. And I believe I've stopped sharing my screen at this point.
Yes,
yep,
you
got it from here.
Okay. Great, thanks.
All right, Mr. Tanner, you are muted, sir, so if you could go ahead and unmute yourself. And I have you as a presenter.
Great, thank you. And I hope everybody can see my screen now.
You're actually coming in loud and clear, and yeah, we can.
Excellent. Yes, thank you for having me. It's great to see everybody and you all moving forward. I know there are many people who can't move forward in the same way right now, and definitely in my thoughts as well. I'm here to give an update on the groundwater modeling. I spoke to you in January when nice to be able to visit with you and provide an update on that, on the groundwater model that we will be using to simulate the climate change scenario that Sean described, to evaluate projected conditions as you plan for your future sustainability with this GSP. So the objectives tonight are to go back to January, review very quickly the update to the model that we have included to better be able to use the model for GSP purposes. And we've also done a little bit more beyond that. And so I'll provide an additional information on what else we have done since January on just improving the model's functionality. But most of our efforts in January has been on model calibration. So I'll be providing an update on that as well. Model calibration is still in progress. There are some areas where we think we can make further improvements on the way the model simulates historical conditions, but I'm going to share where we are now, where we're doing well, and kind of point out what we're still working on. And finally, preview next steps. I already previewed that preview and talking about there is a little bit more calibration to be done, but then what do we use the model for? And a lot of that is incorporating the scenario that Sean described in doing future, in simulating future conditions, but it's also providing information for the GSP about present and historical conditions so you can compare how things will look in the future to how things will look, has looked to date with respect to how the model is simulating things. So I'm here to review and update on the model improvements. And so one of the main things was to expand the model to cover the basin, and because that's a requirement for Sigma with the GSP, that you have a model that represents the whole basin. And so the four corners of the basin were not included in the previous version of the model. And so we had to expand the model to cover those areas and expand the geology, the representation of the geology to include those models, include those areas. And so we did do that. Another big part of it was to incorporate consistently how the representation of the boundary with the Mid-County Basin was represented or is represented. And that boundary was main part of basin boundary modification requests that both the Santa Margarita Basin and the Mid-County Basin GSAs made to define the basins that provide the groundwater resources for your respective communities. And so we made changes to the model to be consistent with how that boundary is described in what was submitted to DWR. The other thing very relevant to what Sean was talking about, we needed to make adjustments to the model to better be able to take the information from the GFDL scenario and represent it for future conditions in the model. And so that was revising how rainfall, evapotranspiration estimates, and recharge are calculated and input into the model so that we can take that information from the GFDL scenario and implement it into the future conditions. And so the way the historical run and the future run are set up is that they're consistent in how they take this climate information so that we can be able to compare those future conditions, those historical conditions in a better way, and be able to implement that future climate scenario. Another thing was to improve estimates for groundwater pumping. That included additional data for public water supply wells, as well as more comprehensive mapping of domestic pumping. And one thing I should say is that with respect to the question earlier about how climate change could affect consumption, we can incorporate that information into our future scenario where the climate change information affects what is assumed for irrigation, for instance, and would affect the estimates for groundwater pumping in the future. So that is the kind of effect of climate change that can also be incorporated into future scenarios. The other thing we did with the expansion of the model was to expand the stream network to make sure all the streams represented in the newly added areas of the basin are included in the model. And as part of the ability to simulate climate change, the runoff calculation was revised so that all the climate information affects the runoff and the recharge in a consistent manner. The main new addition as far as model functionality that's been added since January is that we've connected spring flows to streams. So the model has always identified areas where springs occur, where water is surfaced, but it has never routed them to the stream tributaries. And there has been observations that does occur. So we did incorporate that, where that flow from the springs is added to stream tributary. So that's the main change that we've added since. Before I move on, I just want to make sure I answer the previous question about sea level rise. And with our basin boundary, our basin is not connected directly to an ocean boundary. So unlike the mid-county basin, sea level rise shouldn't have much of an effect directly on the groundwater resources of the Santa Margarita Basin. When you're concerned about seawater intrusion like they are in mid-county basin, you need to address sea level rise in your GSP, but we shouldn't have to for this GSP, and it isn't represented in the model because it's not directly connected to the ocean boundary. So before I move on to discussing where we are with calibration, I think this is a good time to stop for any questions.
I don't see any questions in the chat feature. Thank you.
All right, and just to check the phone real quick, Director Moran. Director Moran, do you have any questions, sir?
No comment.
Oh, gotcha.
So we'll move into update on the model calibration. And this has been an effort that we have mostly spent our time on with the model since January. As I mentioned before, this is still in progress. I think we are getting close, but there are some areas that do need more attention, as you'll see in a bit. So model calibration, why do we do it? We want to use this model for predictive purposes. We also want to use it to be able to accurately represent the water budget and other conditions of historical and current time periods. And so we need to demonstrate that to use it for those purposes, we want to demonstrate that the model can simulate what has been observed in the past. And how do we do it? We adjust aquifer properties and boundary conditions so that the simulated results from the model match observed groundwater levels and surface water flows. And you can see that example hydrograph here, where the black dots are the observations and the blue line are the simulated values. We're trying to match as closely as possible the blue line to the black dots in as many representative wells as possible. These figures like these or graphs like these will be provided throughout this section of the presentation, where the black dots, connected black dots represent the observations. The blue line represents the current results of the model. And for reference, the gray dashes are results from the Kennedy-Jenks model. That was the previous version of the Santa Margarita Basin model. I'll be presenting the results from the model by principal aquifer, how the GSP requirements or regulations request things be organized, and also represent the different parts of groundwater supply resource for your basin. And so just as an example, along this purple line that represents a cross-section from the northwest of the basin, part of the basin, to the southeast, you can see the different principal aquifers in cross-section, where the yellow area is the shallowest Santa Margarita sandstone, the gray is the Monterey, the brownish part is the Lompico, and this cross-section shows 3 different units of the underlying, or the lowest butyl. So starting with the shallow Santa Margarita, this hydrograph in the Olympia Mission Springs area shows an improved fit with our changes to the model, where our model, the blue line, matches fairly well the observations over time. And in the Pasatiempo area, also shows a good fit with the level of the model simulation matching the observations. As we move down into the Pasatiempo area and also down into a deeper aquifer, the Lompico, we simulate long-term trends, do a good job of simulating long-term trends in the early part of the period where there was a decline in groundwater levels, and then it is stabilized at the lower levels since then.
Can you use your phone?
And also, one thing that we want to look at is the vertical gradient between the shallow aquifer and the deeper aquifer. And in the Pasatiempo, that gradient is consistent with what's been observed in the past. So on the left is the observations in the blue line, the shallower Santa Margarita, and the deeper Lompico. The simulated values have a similar downward gradient, where water is higher in the shallow aquifer and lower in the deeper aquifer, such that flow would be from the shallow aquifer to the deeper aquifer. And the difference between the two levels, between the two aquifers, are similar to what we observed in the past.
And Cameron, before you get too far, Lois had a question. I just want to keep it fresh in her mind and my mind.
Definitely, I can take that question.
I might kind of be off base here, but a little earlier there was on climate change, it was talking about wildfires, and you're talking about stream flow and surface water and groundwater. And I mean, we've had a catastrophic fire in the San Lorenzo Valley Water District. We have so much damage, and I don't know about, I assume that even though maybe the stream water's been polluted with ash and whatever, I don't know if it affects flow, but then we've had trees going down. If trees are in the stream, I'm just wondering how this disaster is going to play out. I can't see it getting better overnight. And so I'm thinking, what's our stream flow going to be like? What's our surface water going to be like? Because we've always had like 50% surface water and 50% groundwater, and it's almost like everything is changed. And how does that fit in, or does it even fit in with your calculations?
So it hasn't fit in with the calculation. it we are simulating through 2018 or so. We try to represent the land cover that has existed historically. We don't get to the specificity of saying how that land cover has changed with specific events over time. I think it is reasonable to assess, to consider for our future simulations what land cover is expected to look like into the future and whether some adjustment to the land cover should be made for those future simulations. And that could potentially be done, but it be represented in what we think, how much runoff occurs in areas. If there's less trees, for example, you'd expect more runoff. You'd expect less evapotranspiration, but maybe that would result in less recharge. So that's something that could be considered, and I think the recent events point to at least giving that some thought as we move into representing future conditions.
Cameron, Sean thinks he could weigh in and offer a little assistance for Lois's question.
Sure, I'd love to have assistance. Go ahead, Sean.
Okay, yes. I'll just provide a little bit of context in terms of what some of my colleagues have learned over time, evaluating post-fire effects on runoff. Starting with the Marble Cone Fire, some of you have heard from Barry Hecht in the past. Barry worked on evaluating conditions after the Marble Cone Fire in the Carmel watershed, for example. And what he observed there, and others that he worked with observed, is the effect to runoff lasted about 1 to 2 years. And in general, the effect was higher peak flows for a given rainfall intensity, which then would translate into less water making it into the ground. That happens for a variety of reasons, as most of you, or probably all of you, know why. But in the Marble Cone Fire, the effects were 1 to 2 years. In more recent fires on the California coast, Barry has seen hydrologic effects that extend up to 2 to 3 years in terms of affecting the average runoff condition in the watershed. So you can expect changes to runoff for a given rainfall event to last anywhere from 2 to 3 years. And broader, people who are working on fire, and I should say that fire and hydrology, the coupling of the two, and the disaster or the effects it has on communities is a very growing field of research in the earth sciences very rapidly. Many people are getting interested in it, of course, because the fire threat within the western U.S. is much higher than it used to be for a variety of reasons. But I think for your question, what we can think of is in terms of the basin producing runoff and the average rates that water gets into the ground and leads to stream flow on the surface and the opportunity for recharge. On average, or in general, we can expect effects that last 1 to 3 years.
So, all right. If we get heavy rains, like is pretty normal around here, then we're gonna have mudslides. And I mean, we're in a mountainous area. And I know you guys don't have a crystal ball, but it's concerning.
Very concerning. It's absolutely.
Thank you. The other thing I would like to add there is that I think Sean mentioned the relatively short-term effect on runoff of fires, but certainly if the fires are more frequent, then those short-term effects could add up. But one thing that you are required to do and afforded to do is to reevaluate on a regular basis kind of the assumptions that go into your planning. And so you're required to do a 5-year update after this groundwater sustainability plan. And if you learn new conditions that look more permanent and have an effect on your planning for groundwater sustainability, this is something you can continue to revisit based off of what has occurred in the meantime.
And I had a very quick, much more pedestrian question than Lois's. When you were showing the different aquifers, I might be having a little brain lock here, but I don't recall the Butano being split up into 3, or maybe I'm just forgetting. What's the reason for that?
Georgina, do you want to chime in here with how that has been developed over time? They are treated as separate layers in the model.
So yeah, the Butano has an upper, middle, and lower member, and so and they're very thick, and so the model, it doesn't handle. It's not good to have these really thick if we just bundle them all together. So they are split. In fact, the Monterey formation, the shale formation, is also thick. It's split into 2 as well. So that's when you see the layers. Each layer doesn't correspond exactly to a geological formation. Layer 1 is Santa Margarita, yes, it does, but some of the others are split up.
Okay. Thank you.
And just because we're pausing for questions here real quick, Director Moran, sorry to keep singling you out, but just checking to see if you got any questions on your end.
No question.
And then Rosemary popped in with a question.
Actually, I was going to make a comment about the surface water flows, and Sean is correct in the sense that we have there's quite a bit of research going on about the relationship between fire and hydrology of various sorts. So the city is really putting its arms around that information kind of as we speak, and would be happy to share both the watershed process sort of state of the science summary memo that we're working on, one related to water quality and treatment changes, and kind of one related to, you know, sort of general action planning. So we'd be happy to share those with the San Lorenzo folks if they're interested in looking at that information pulled together the way we're planning on doing it.
Okay, thank you, Rosemary. And Ruth popped in with a question.
Yeah, I'd like to know what the difference is between the physical characteristics of the 3 parts of the Butano. Is there a semi-porous aquitard, or are they different crystal sizes? What's going on?
Yeah, I don't know exactly, but generally in geology, they're split based. It could be based off different, slightly different environments that the sediments were deposited, and this is a sandstone. So you know, you need to be able to distinctly see they are different. Sometimes color can be the difference. Sometimes they find upwards or downwards, but there are always geological reasons for the USGS to separate them out like that.
Okay, thank you.
You're welcome.
Okay. Cameron.
Thank you. And I may have to phone a friend again later in this presentation based off the questions, but we will continue with the discussion of the model calibration of the groundwater levels. So for this hydrograph in Camp Evers area in the Monterey, this, even though there are parts in time where the groundwater levels don't match the observations, the model now simulates the long-term pattern in an improvement of that simulation of the pattern from from the previous version of the model. We also look at simulated vertical gradients in this area between the shallow at Santa Margarita and the Monterey below it. There was an observed downward gradient in this area as well. As you can see, the blue dots on the left higher than the gray dots. But we're actually simulating more of a vertical gradient than was observed. And even though it's still downward, it's a greater difference in groundwater level. So, this is one of the areas where we will pay additional attention to as we continue with our calibration work. In the Lompico area, in the same area in the Lompico, as we go down in depth into the deeper aquifers, the model is simulating the long-term pattern of the drop in the early period, and then more stable since then, but with some variation over time. Now, in the Santa Margarita, in the Scotts Valley area, the model versions have underpredicted observed values, so we have been able to raise the simulated groundwater level with this version of the model. The Lompico hydrographs for Scotts Valley is an issue we need to pay more attention to with or additional work on with the calibration, in that we're not simulating the observed drawdown that is observed in the last 15 or 20 years. And so that is part of our current efforts. And then in the Bitano, pretty consistently under-predicting groundwater levels, and this, I think, is also possible to be improved. Overall, though, if you look at the summary of the observed water levels versus what the model is simulating, I mean, these are basically pairs of observations and then what the simulation says at the same time and place. A perfect fit would fall along this one-to-one line. And for the Lompico, Monterey, and Santa Margarita, these pairs generally fall along the line. As we were generally under-predicting groundwater levels in the Bitano, you can see how it diverges from this green X's diverge from that one-to-one line. We use these maps to kind of identify where in calibration more effort needs to be undertaken, where basically the larger dots are where the model is farther off from the observation. We could separate into the dark blue, where the simulated values are under-predicting the observations, and the lighter blue, where the simulated values are over-predicting the observations. And then we do that for each of the aquifers. There isn't as much data in the Monterey as Santa Margarita. And in the Lompico, you can see some of the Scotts Valley area, which I pointed out earlier, which we are working on. And then the Bitano here, where the blue areas where we have been under-predicting the observation. The overall comparison with the KJ model, there are more areas in the darker blue where we have improved the model, but there are still some areas that don't perform as well as the KJ model. One of the things that we wanted to be better represent is the drying out of the Santa Margarita aquifer over time. And the current version of the model does simulate a larger area of the Santa Margarita that is that it dries out by the end of our run, which is water year 2018. I think here would be a good time to stop for additional questions as I kind of transition from the groundwater level calibration to stream flows.
Nothing's in the queue. So far, so good, Cameron. Director Moran, maybe?
Yes, I have a question.
Okay.
Yes, so how do you correct the model? Without too much technicals, but I just wanted, you're saying you're going to correct the model or it needs alteration. How do you do that? What inputs are you looking for?
Yeah, so I will show kind of the different aquifer parameters that we do change in a little bit. They're basically values that represent one, how the aquifer materials transmit water, whether it more easily transmits water or less easily transmits water, and how water levels respond to stresses and how water levels change over time. There's a parameter that reflects that, and I'll show a little bit about how that looks in the basin in a little bit.
Thank you.
Okay, and we have Jack Dillis has a question also.
Yeah, I'm wondering, can you use different models for different aquifers? And I know you showed something that showed what if you put it all together, I think, but I'm trying to get my head around, can it be mix and match with these different looks that we're seeing?
Well, I think what we don't want to mix and match because the aquifers are connected. There is some vertical flow between aquifers, and so you want it to be able to represent any connection that has as well. So it is important to have a model that represents all the aquifers together.
That makes sense. Thanks.
And Angela has a question.
Yes, I can.
All right, yep, Director Franklin, I got you unmuted there.
Okay, thanks. It was kind of in relation to the same question that Jack just asked. I mean, I know some of the aquifers are connected, but I thought the Santa Margarita, which is the most shallow aquifer, is not attached to any of the other ones. And so I kind of feel like, I mean, if they are connected, I could kind of see that lumping them all together, but if they're not connected and they behave completely differently, which I think the Santa Margarita does, shouldn't we consider that to be a separate model?
Well, we do consider it separately. It's a separate layer in the model, and so it is somewhat separate. And I think in earlier slides where I showed differences in groundwater levels between the Santa Margarita and underlying layers. Let me get back to one. Such as here, and they are able to represent the different conditions in the different layers. So the Santa Margarita is treated differently from the Monterey in this case. But the Santa Margarita does overlie the Monterey, so there is a potential for flow to go from the Santa Margarita to the Monterey, and we want to be able to simulate that possibility.
Okay, thank you.
So now we'll move on into kind of calibration of stream flow in the model. And this, where the model is used for stream flow, is to estimate kind of historical and current depletion of related to pumping of stream flow, and then also inform development of sustainable management criteria for depletion of interconnected surface water. So again, we're trying to simulate, have the simulation match the observed values. Boulder Creek here is way in the very upstream portion of the upstream of San Lorenzo River, so very upstream portion of the basin. In the area also up gradient in the Lompico Creek, we simulate stream flow above about 0.4 CFS, but in what you'll see in many of the upcoming slides, the very low stream flows we do not simulate with the model. Do have a good fit for the stream flow at Diana Creek at LaGuardia, where the stream flows are higher in observations and the simulated. But as we get down into towards the USGS gauge, the lower stream flows and aren't simulated. And this is where one area where what we're working on. And what we really want to do is be able to simulate how stream flow drops off more than what we're seeing here in the gray line. Now, it may not be realistic to simulate precisely the lowest flows that you see here. Once you get under 1.5 CFS, that may not be realistic with the construction of a model and not be able to get that exact. But we want to be able to show how stream flow drops off over time as flows drop during drier conditions. A good fit of stream flow for Bean Creek at Mount Herman Camp, although here some of the lower flows are not simulated. And then more obviously at Bean Creek and Mount Herman Road, the lower stream flows, even above 1 CFS, aren't simulated. So this Bean Creek and the Zion Creek from below, that's what we have a fair amount of focus on right now in improving. At Carbonera Creek to the east, is a pretty good fit for the stream flow with the simulated values and observation, as well as San Lorenzo River at Big Trees. Again, these are high, and this here, the higher flows, the flows are higher, the model does perform better in fitting to the observations. So getting back to Jack's earlier question, or the earlier, actually that was Rick's earlier question about what we changed in the model to have it represent observations earlier, observations better. And so one thing that Georgina explained way back last fall in the Model 101 presentation are, what is included in the model to represent the subsurface condition. And there are certain properties of aquifers that represent how groundwater is transmitted through the aquifer. And one of the main one is hydraulic conductivity. And basically, higher hydraulic conductivity means the aquifer transmits flow a lot easier. water just flows a lot, goes through faster, these higher hydraulic conductivity. So those are be more like sands and gravels. When you get to finer grained aquifer materials like silts and clays, the hydraulic conductivity is lower as the water is not transmitted as easily. So the values representing the hydraulic conductivity affecting both flow in the horizontal direction and flow vertically, specifically vertically between the aquifers, so between, say, Santa Margarita and the Monterey, we are changing to represent historical conditions better with the model. So there's pretty high hydraulic conductivity in Santa Margarita. So you can see in many areas here there are fairly low hydraulic conductivity represented for vertical flow, so flow between the Santa Margarita and the underlying unit. And when they're lower, it's more separated, to get back to the earlier question. Going down.
Great.
Through,
oh, sorry.
Was there a question?
There is, but just continue for a little bit more. Just finish your thought.
Okay, great. Going down the Monterey, generally lower hydraulic conductivity are represented in the model. In Lompico, it's a medium level. The colors represent the horizontal conductivity, and the labeled values represent the vertical conductivity. And then when we're in the Butano, those conductivities for all upper, middle, and lower are all relatively low. I think this could be a good time to take the question.
Yeah, two things. One, Sean has signed off. He's thanking us for our attention and keeping us all in his thoughts in the days and weeks ahead. And now Ruth has a question.
I didn't get to see the Carbonero Creek diagram enough to understand why it was lines rather than a solid graph. Does it dry up?
Right. I think you're referring to why the gray line, the simulated values are disconnected.
Yeah.
Yeah, there are gaps in what's simulated. So when there isn't data, it's basically the flow in the model goes to zero. And so maybe an observation, I think if you can see my mouse, I'm pointing to a point here. The observation of flow during that month averaged a 0.01 cubic feet per second, but the models for that month simulated zero. I would say that the model is doing pretty well simulating the very low flow that occurred, because this is an average over the month, so many days maybe had zero flow, but it did have some flow in some days, and so it averaged out to 0.01. So where the line disappears, it's basically the model is simulating no flow, and it's pretty consistent with the low flow that we see during this time.
Okay, thank you.
Georgina has a comment.
I think I need to point out that all of these charts, these streamflow charts, are on a semi-log scale. So if you look at the vertical axis on the left side, you see that it goes, say, from 1 to 0.1. And so those are extremely, extremely low flows that are very difficult to measure sometimes. And like Cameron says, the model has some trouble with it. So bear that in mind when you look at these. It's not, it's not the kind of scale that you're used to using where every line is an equal interval apart, the grid lines on them.
And we show it that way because we do want to be able to look at the low flows more closely. If you did it on a regular linear scale, it would be dominated by the high flows, and you wouldn't be able to look at the low flows at all. It would look pretty close And so we want to look at the low flows more closely, and that's why we scale it this way.
Okay, and Gail's got a question.
Yes, thank you. You noted that the model doesn't work very well at these low flows, and I can appreciate why that might be. But is the point at which it doesn't work very well, how does that relate to the minimum flows that we have to keep in streams for the coho and steelhead salmon? In other words, one of the things we really need to be able to model are summer low flows. And so how do you do in your models at the levels you need in streams to keep the salmon able to do what they need to do?
Right, and I think that's going to require coordination with the surface water working group to see what low flows they're looking at. I mean, one of the main uses really of the model is to try to estimate depletion from pumping, and for that, I don't think you have to be able to simulate the lowest flows, but there has to be enough of an intersection with what the surface water working group is looking at for flows, maintaining the flows in those creeks as well. So that's why I think that it is worth the effort to improve it. But I think at the very lowest flows, that's not going to be that may not be simulated, and we just have, when we look at these results and wherever it ends up, we have to recognize what it's able to do and what it's not able to do. Right. And if we're saying that, we need to maintain 0.5 CFS, for example, and our model never drops below 1 CFS. We cannot look at the model and say, the model says it maintains above 1 CFS. We're always above 0.5. Everything should be good. Right. So we just have to recognize what it does. But on the flip side, if we say we want to make sure that depletion isn't increased a certain amount, and we think that depletion occurs mostly most of the time it is above 1 CFS, and that our estimate of depletion is overall representative, we can make those statements that the model is showing that with these projects and management actions, this improves. So that's why I think it's really important, even though this isn't a finished product, to be able to talk about, hey, the model is not going to be perfect. It's not going to represent all conditions. We need to recognize where it doesn't do as well and use the results accordingly.
Agreed.
We have Rosemary and then John Ricker. Rosemary?
Yeah, I just wanted to make the comment that in the part of the basin that we're talking about here, the San Lorenzo River Basin, apart from a bypass flow requirement that the city is agreeing to at the Big Trees gauge in the Felton area, there really aren't required in-stream flows. So that's not to say we shouldn't be planning for maintaining flows to support the fishery, but there aren't, required in-stream flows in that part of the basin. The city will have a flow requirement at Big Trees gauge for a bypass flow of 40 CFS, and then a various downstream at our Tate diversion for bypass flows there. But that's the result of, as Sean mentioned earlier, some 14 years of work of figuring out what the flow regime ought to be and working it out with the fisheries agencies. So if there were to be some plan to go in that direction, it's quite a bit of work ahead to get there.
John?
Yeah, the comment I wanted to make was that low flows are influenced by a lot of things besides just groundwater contribution, and I'm thinking that maybe the model really isn't able to capture some of those effects. Riparian evapotranspiration from the riparian quarter, or underflow, where the flow is actually moving through the stream bed and not able to be measured, and also, you know, potential surface diversions where people are pumping water out of the streams. So those would all be factors that would result in a lower gauge flow than a modeled flow. And it's just one of the things we have to grapple with in trying to deal with this whole issue of surface water depletion, is that there are many factors that affect flow other than just the groundwater contribution.
Okay, thanks, John.
Yeah, thank you for those comments.
And Director Moran, just to check in with you, do you have any questions, sir?
No question.
Okey doke.
The other property that main property that we adjust for to represent groundwater aquifers are storage properties, and this is basically how groundwater levels change over time as water is removed from the aquifer or added to the aquifer. And this figure in the lower left corner was a figure from the 101 Model 101 presentation from last fall, but basically how groundwater levels change as water is removed or added to the system differs whether the aquifer is unconfined or confined. And if it's unconfined, that means that the groundwater levels are below the top of the aquifer and our atmospheric pressure, while if it's confined, groundwater head pressures are under pressure and the groundwater heads are above the top of the aquifer and they're being pressurized by the above aquitard. So they're different. In unconfined aquifers, it's called specific yield, that represents how groundwater levels change with how much water is removed from the system or added, while in confined aquifers, it's called specific storage. We found that specific yield, represented by the colors, is pretty important to representing how groundwater levels have dropped over time historically with the depletion of groundwater levels. And to represent that pattern has been groundwater levels as those aquifers, like the Santa Margarita, has drained and dried out. So it's been an unconfined condition. And so the model does include quite variable specific yield values in the Santa Margarita, fairly low values like colors in the Monterey. And in the Lompico, there's been a variable specific yield values, but here is one area where we think more variability could help us represent historical observations better in the Lompico. And then the Butano, being the lowest aquifer, mostly is not unconfined, so specific yield isn't as important there. Before I go to the next steps, are there any questions?
Good.
Okay, so with next steps, we had a uncalibrated model and had all the different information to incorporate into the model. We're pretty far along on the calibration, and but I think some more work can be done on calibration to improve the model and have it more calibrated. But once we have a calibrated model, and ready to move forward, we'll use the calibrated model of historical conditions to provide historical and current water budgets for the GSP. It can also be used for estimates of stream flow depletion. So that's for historical and current conditions. For future conditions, we'll take additional model inputs, such as the climate change scenario that Sean described, as well as any other information about changes to land use. We talked about a little bit about potentially considering land use cover changes, but also model inputs like projected water demand, and then run future simulations. We'll run one without projects and management actions that are included in the GSP, and then one or more with projects and management actions that are included in GSP. So you can see the expected benefits of those projected management actions, and also provide future water budgets for the groundwater basin. So those are our next steps with the model, and I'm sure I'll be back describing the results of those in coming months.
Okay, great.
What other questions?
So there are no current questions in the board. Maybe, Nick, this is a good time to.
Yep, let's just go ahead and start. Director Moran, if we could just check with you real quick. Do you have any questions, sir?
Thank you, but no.
All righty, and
Before we do this, Nick, I did see Director Engfer has a question.
Yep.
Sorry.
Yeah, and Cameron, apologies if you said this and my brain had just swapped out, but what's kind of the timeline for finalizing these various next steps you've outlined?
Well, as far as calibrating the model, that's over the next 1 or 2 months. Then we really do need to use it for all the purposes that are shown at the bottom of the slide. And then we can then use it for those historical current water budgets. I'm not sure about the schedule for presenting that. Maybe Georgina can chime in on that. And then we would go ahead and set up the model for projected conditions without projects and management actions. But I think there will be a little bit more work towards the end of this calendar year about what defining those project management actions. Georgina, do you have any other information about the plan schedule there?
Yeah, I prefer that we were using the calibrated model was done and water budgets, we could start extracting those at no more than 2 months out. We need to get those done pretty soon. And Cameron's right. We can run the predictive model once we integrate climate change and any other changes that we foresee in the future into the first model run, predictive model run, where we have no projects and management actions, but there is still quite a lot of work to do on projects and management actions till we can get that scenario to compare to the baseline of not having those projects and management actions. Hopefully that
Great.
answers
Thank
the
you.
question, Doug.
Okay,
Yes,
Nick, so let's go to back to the public.
Okie doke. Let's see here. So if you're a member of the public and you are joining us via web or via the GoToMeeting app at this time, just go ahead and either put yourself in the questions queue or just go ahead and unmute and say what you have to say.
This is Gail speaking, and I'm just a little worried about the timeline. I saw Sean's talk in December, and this one didn't really seem all that much different. And the results he showed were largely for previous work that was done for Santa Cruz. So have they been contracted to actually produce something directly for our basin? And if so, when is that going to happen?
I can answer that. So yes, they are going to be providing the input to the model that we need. We need temperatures and precipitation that we will use in the predictive model runs. So that's what they're going to be providing us, but we're getting a bit of a saving because they have already done a lot of this work for the city of Santa Cruz. And we don't want to run a different climate scenario than what the city of Santa Cruz has done. We kind of ran into that issue in the Mid-County Basin. And so all the water agencies have agreed that this is a good scenario to go with. And in fact, I think Sean may have already provided that data for us. So we're really waiting for the calibrated model. We can put the climate change information in, and we also have to work closely with the agencies to figure out what the projected pumping is that they expect to have over the next 50 years, which is quite an ask. So that's also something that's going on.
Okay, thank you. Okay. Cameron, thank you very much.
Real
Thank
quick,
you.
let's just do one last sweep there. I'm just going to double check if there are any more public comments here. And again, as of right now, the only folks who are calling in are both directors. One of them's both of them are alternate, one of them non-voting today. So it looks like we are good to go for public comments at this time.
Okay, well, once again, thank you, Cameron. Look forward to seeing the final calibration.
Welcome and thank you.
All right. Well, that was a lot of information. We went a little longer than we had hoped, but not too bad. Does anyone have anything more to add, or should we go to item 4? Which would be adjournment.
I was glad that Jack didn't start letting out those little barking noises until the end. And I'd like to move we adjourn.
Okay, see, a sensible man. That's why we want you to stay on the board, Eden.
I'll second. It's Ruth.
Okay, Ruth, so Eden and Ruth. And I'm just going to assume everyone is in favor. So just because this was so much fun, let's do it again tomorrow night.
Oh, boy.
Same time,
yeah,
same place.
Yeah, quick admin note here. I should have this meeting up on YouTube tomorrow, hopefully before lunch. If you're voting against adjournment, just let me know.
Okay. All right. Thank you, everybody. And be safe. Take care.
See you tomorrow.
Okay.
Thank you. Bye.
Thanks, everybody. Bye-bye.
Bye-bye. Thank you, Nick.